Okay. Hi, everyone. My name is George, and today I'm going to be talking about the foundations and anchoring systems for offshore wind turbines. So just going over the schedule, we're going to talk about what they are briefly, then we're going to talk about the history of foundations and anchors, and then we're going to get into the typologies of foundations and the different anchoring systems, and then discuss the environmental impacts of the foundation and anchoring systems for offshore wind farms. So foundations and anchors, broadly speaking, are just the things that kind of take the loads, the vertical and horizontal loads of the turbine and transfer them to the seabed. For stationary structures, so things that are connected directly from the nacelle all the way rigidly down to the seabed, they're relatively interchangeable terms. We'll just refer to them as foundations. And then for floating offshore wind turbines, anchors are specifically the things that are in the seabed. The foundations are specifically what's connected to the tower and eventually the nacelle. And then they're tethered to each other or moored to each other via a cable or chain or something like that. And the reason why we care a lot about foundations and anchors is because they make up over a third of the total cost of the entire offshore wind farm. So originally, a lot of the technology for the offshore wind industry was borrowed from the oil and gas industry, which kind of gave it a bit of a springboard. This image on the right kind of illustrates that a little bit. You can see on the right, we have this offshore oil rig, which is built on what's called a jacket foundation. It's kind of a series of cylindrical tubes that's assembled into a truss structure that's known as a jacket. That's very common for offshore oil rigs and also fairly common for offshore wind farms. Early offshore wind farms use gravity and jacket foundations, which we'll get into later. And then kind of in the infancy of offshore wind, monopiles have become very, very common up until recent years as well, just because they're very simple, relatively inexpensive, and the installation process is quite simple. However, as we're venturing into like much greater depths, we have to begin investigating new foundation technology that's a little bit more exotic, a little bit more efficient, things like that. And the general trend of the offshore wind industry is that turbines are getting larger and going further offshore. So the first offshore wind farm, built in 1991 in Denmark, used a gravity-based system. It was, I think the depth was no more than 10 meters for this wind farm. It was actually just decommissioned in 2017 after 25 years of service. And it had a capacity factor of 22.1%. So not that great. Over the past 20 or so years, we've noticed a trend of turbine power drastically increasing, and directly correlated with this increase in turbine power is an increase in the rotor diameter. Rotor diameter is kind of directly related to the loads that are going to be inflicted upon the foundations, just because, you know, for the horizontal loads, for example, the disk area is going to increase the horizontal loads, and then as the turbine is getting larger, the generator is going to weigh a lot more, and the nacelle and the tower are just going to weigh a lot more vertically. So along with this, we have to really rethink how we do foundation design. Also, another trend that we've noticed is that turbines have been getting located further from the coast and in deeper waters, which is kind of what this general trend of green blobs shows. Green is indicating the more recent wind farm installations, and they're also getting a little bit larger, which is what I previously mentioned. So what are the types of foundations? There's 8 types that we're going to get into, and I'll try to race through these a little bit because there's a lot. So first we'll talk about the monopile. Monopiles are very cost effective up to 40-meter depths. However, they've been proven to be feasible up to 60 meters. They're a single large diameter steel pipe, also known as a pile. And these piles can get up to 10 meters in diameter and 4 inches thick in the walls, which is crazy. They can weigh between 600 and 2,000 tons. They're driven into the seabed by what's called a pile driver. And these are either vibratory or hammer, which actually has a lot of negative acoustic effects for the marine life. And the soil resistance at the end of the pile, as well as the friction on the sides, are what carry the vertical loads of the turbine. And then the horizontal loads are just carried by the monopile's resistance to bending, which is pretty cool. They're ideal for sand and clay seabeds because of their method of installation. And typically they're prefabricated in a shipyard or in some other facility, transported on site. They're raised vertical by a specialty installation crane and vessel, and then they're sunk into place and pile driven to the appropriate depth. Jackets are the other technology that I mentioned that was borrowed from the oil and gas industry. They're cost effective between 20 and 50 meters. And as you can see on the right, they're just lattice truss structures, very similar to oil rig tack, as well as, maybe railway bridges, things like this. We're familiar with trusses. They're formed from tubular steel up to 3 meters in diameter. And what's kind of unique is that they have this steel transition piece on the top of the truss that distributes the weight from the tower down through the truss structure. The vertical loads are taken by the piles. They're oftentimes anchored to the seabed with piles. And what's cool is that the horizontal forces, instead of creating a bending moment, create what's called an overturning moment. And this is mostly counteracted by the piles and the turbine. The center of gravity, as long as it's, if you'll recall from statics, as long as that center of gravity is within that platform on the bottom, it's not going to tip over. So it's super, super stable. Because the piles are much smaller diameter than a monopile, they can go in stiffer clays and medium to dense sands. And these are typically going to be built in a shipyard, turned vertical on site with controlled sinking or a crane, and then anchored to the seabed. Tripods are kind of a hybrid between jackets and monopiles. They look like jackets under the water, and then they look like a monopile from above the surface. Tripod means obviously it's going to have 3 piles, while jackets can oftentimes have 3 or 4. At the base, we're going to have kind of like a diameter of between 20 and 40 meters. So these things are pretty big, really strong. And the rest is all identical to a jacket. Tripiles are, again, another kind of hybrid system, cost effective between 25 and 40 meters. They're going to have 3 piles that are driven into the seabed. What's cool about this is that the piles, again, are going to be smaller diameter than a monopile. So they're a little bit more versatile in the types of seabeds that they can be installed in. What's also nice is that they can be prefabricated in separate pieces. And so transportation logistically becomes a lot less complicated, because you can imagine that these piles weigh a lot less than one monopile. So that all kind of helps bring the costs down. Jackups are another technology that is directly borrowed from the oil and gas industry. This is what a lot of the kind of transportable oil offshore drilling rigs are based on. So you manufacture this whole floatable hull, and then you have these piles or legs, as they're known, that can be elevated out of the water, and then you can tug this hull to whatever location you want. And then the hull actually kind of has a built-in pile driving system built in. So you lower the legs to the seabed, you drive them in as deep as you can. And when you're doing this, you actually pump in water to the hull to kind of increase the effective weight of the ship, which allows you to drive it deeper into the soil. Once you're satisfied with how deep the piles have been driven into the seabed, you elevate the hull, pump all the water out, and then you have a super solid foundation. This third footing that's shown in the back, sometimes there can be a third and a fourth, is actually only used when you want to move the foundation. And this is what's kind of the main advantage of a jackup. It's very transportable, relatively speaking. So when you want to move, this footing goes down and it has a really wide surface area on the base of it. And this kind of allows you to lift the piles that were previously driven into the seabed out of the seabed, and then you can be tugged to a new location. This technology has only been proposed up to 100 meters. It hasn't actually been tested anywhere, and I think that's because it's fairly expensive, because you have to build this pile driving system into every single turbine that you want to install, which just isn't super practical. Suction buckets are really interesting and where a lot of development is actually being put into right now, because they're fairly versatile into the type of soils that they can be installed in. They have been demonstrated at up to 10-meter depths. However, there's a lot of literature that proposes them at much deeper depths. and they use what's called a suction Kaizen to drive the base into the seabed. And so the way that this works is just kind of simple hydrostatics. It's this cylindrical steel object with an open face on the bottom, and you lower it into the water onto the seabed floor. Because it weighs, 500 tons or so, it sinks a little bit itself into the seabed, and then you begin pumping water out of the suction Kaizen, and the hydrostatic force of say 10 to 50 meters of a water column pushing down on the suction Kaizen just drives it into the seabed, kind of like a pile driver. Because the diameter is much larger, it doesn't actually have to go quite as deep as a pile, and so this is pretty cool. There's some research groups at Purdue University and University of Maine that are looking into 3D printing these suction Kaizens to kind of lower the costs. So this is a really cool technology that I would totally recommend keeping up to date on. Gravity-based systems are pretty archaic. They're still used in shallower depths, but they have some of the largest environmental impacts associated out of all offshore wind foundations. And that's because they have a really, really large diameter, and they simply work by just kind of being plopped down onto the seabed. And the reason why this is bad is because you have to do a lot of dredging on the seabed to ensure that you have a flat, hard surface. And typically they're going to be between like 10 and 24 meters in diameter, so pretty large. And yeah. And so now we go on to floating offshore wind, which is kind of where a lot of the development is going into right now. And there's three broad categories of foundations for floating offshore wind. You have spars, you have semi-submersibles, and you have tension legs. Studies have shown that offshore wind is feasible up to depths of 700 meters. And I think the limiting factor with 700 meters is just having cables that can withstand enough tension, because 700 meters is, almost a kilometer of cable. That's going to be a lot of weight and a lot of tension in that cable. Now, as I mentioned earlier, there's a distinction between the anchoring system and the foundation system, which is what I'll get into after this. But the installation is super simple. You just kind of tug these floating platforms out the site, and then you attach the foundations to the anchors via cables. Super simple. So the spar system is just a single ballasted cylinder, which extends below the waterline, which is what gives it stability. And the anchoring only serves the purpose of station keeping, so just preventing any movement with relation to the seabed. The cables are at low tension, which is what's known as a catenary mooring system. And you kind of notice this J in the cables. Actually at the base where they're attached to the anchors will be almost horizontal, almost parallel to the seabed floor. And this is just to enable kind of flexibility when it comes to raising and lowering tides, as well as wave activity. What you'll have to do, I'll get into that in a moment. And then we have semi-submersible foundations. And this is going to be kind of like this truss system of 3 to 4 submerged buoyant columns. And then again, the anchoring just serves the purpose of station keeping, and it's a catenary mooring system, so the cables are in low tension. Finally, we have the tension leg system, which I think is cool because it looks like a spaceship. It's a buoyant floating platform, which then gets tensioned under the surface of the water to basically, these tension legs that you see on the right here, they're just cables, but when they're under such great tension, they kind of just serve almost like a tri-pile system. You have these 3 vertical rigid bodies. So this is a super stable system. So now we're going to get into the anchoring systems, and there's 7 anchoring systems. Gravity base is what is commonly used with tension link platforms. It's just a really heavy counterweight. You plop it down onto the seabed, and it resists any sort of lateral or vertical movement. Drag embedded anchors, you probably recognize these from any ship. This is what a lot of ships will use when they want to anchor. You just drop it to the seabed and drag it along, and it embeds deeper and deeper and deeper. What you need with these is you need a passive tension system. So because tension is what kind of maintains this equilibrium of forces and prevents it from loosening, you need to have tension in the system at all times. And so one way to do this for catenary moorings is actually adding like a chain to the mooring system, or you can add what's called a kettle. And a kettle, it's just a weight that you locate along the cable, and it just sort of guarantees that there's always going to be tension in the system. A drive pile anchor is what I was talking about earlier. This is the technology that's used to drive monopiles in. Super reliable because this has been used both in the offshore industry and on land for things like skyscrapers. They're permanent, very precise. They have no creep over the years, and they have really high vertical loading capacities. The main disadvantage is that they're super expensive. Suction kaizens is what I was talking about earlier. It's kind of a long pipe, open at a bottom end. Water's vacated, it gets sucked down. Super cool. Driven anchor plates. If you've ever done any sort of landscaping work, the closest thing I can explain this with is called a dead man. You know, like a plate that you kind of bury underground and you put a bunch of soil on top of it. And that prevents any sort of, say, the wall that you're constructing from tipping over. In this case, it's going to be a plate that's driven into the seabed, oftentimes with a suction kaizen. And then you pull it perpendicular to that major kind of anchor plane that you see on the right here. And then that prevents any sort of movement. We also have a torpedo embedded anchor, which is as cool as it sounds. You have this torpedo that you release, picks up a lot of momentum, and then it actually just drives itself into the seabed, which you'll see right here. So that's another technology. We also have a drilled and grouted pipe, which is another anchoring system. This is suitable for really hard rock seabeds where any sort of like vibratory or impact driven pile system isn't appropriate. So you drill into the seabed and then you inject grouting around. So it kind of like fills all the voids in that hole and kind of increases the friction. And then the apparatus is removed and you are left with an anchor system, which you'll see right here. There. Super reliable, super expensive. And so I'm going to briefly go over some of the environmental impacts of installing offshore wind foundations. So one thing that you might not have considered when thinking about this is that there is tons of marine life between kind of the low altitudes above the ocean and then the shallow waters, which is kind of the range that an offshore wind turbine is going to be installed in. There's three categories of species that inhabit these regions. You have benthic species. These are the species that live on or in the seabed. Then you have soft bottom and hard bottom communities. Soft bottom live in like fine grained sands and sediments, things like algae or sea anemones and burrowing species. And then you have hard bottom communities, things like crabs and mussels and things that kind of latch onto hard surfaces. Then you have pelagic communities. These are things that kind of freely roam throughout the water. So marine mammals, sea turtles, fish, plankton. And then of course you have the avian communities, which are the birds that live above the surface. By installing an offshore wind turbine, you remove soft bottom habitat and then you install hard bottom habitat. And this is because when you put a cylindrical object in the way of a current, it's going to create a wake behind that cylinder. And this wake can disrupt sediment, and eventually you can kind of remove enough sediment that the whole foundation could tip over. Although this only affects like 1% of the wind farm site area, it's still worth mentioning. What's interesting though is that it actually isn't necessarily a negative impact. Multiple wind farms have actually had a measurable increase in biodiversity and abundance on wind farm site areas because of this increase in hard bottom habitats. And this is due to the artificial reef effect. And so the artificial reef effect just increases the surface area and thus increasing the amount of benthic organisms in an area. What I think is really, really interesting about artificial reefs is these depth assemblages that can be formed. So different organisms like to live at different pressures under the water. And so if you think about a region that previously didn't have any sort of vertical structures, that was the pressure. You only had the organisms that could live at, say, 20 meters below the surface. But when you introduce this vertical hard surface, you all of a sudden have organisms that can latch onto a hard surface at 20 meters, 15, 10, and 5 meters. And so each of these different elevations is called a depth assemblage. And that's what you see on the right here. And then the last negative thing to discuss is invasive species spread. So studies have shown that hard structures can be rapidly colonized by invasive species. This is why you have to get your boats inspected before you drop it into some sort of freshwater lake. Many invasive species mature through larval stages, during which they can drift large distances throughout the ocean in the currents. And some papers have shown that hard structures can sort of act as like stepping stones. And so it can colonize one turbine and then another and another, particularly with floating offshore wind turbines, where they'll be assembled in a shipyard and towed out to site. You can have an invasive species that was only located in that shipyard, colonize the turbine, and then get towed out to a remote site. And that is all I have. Any questions?